Hello students, welcome to the class on functional analysis. Today we will study about quotient norm spaces. First we define what is a quotient space. Let X be a linear space and X0 be a subspace of X. Then we consider set of all elements of this form. Class X. This is denoted by class X. Class X is equal to X plus X0. That is, it is a coset. Okay, we consider the set of all elements of the form class X where X belongs to X0, and we denote this collection by the set X by X0. Now we define two operations on this collection, that is addition and scalar multiplication. The addition is defined as for two elements class X and class Y. In the set X by X0 we define class X plus class Y is equal to class X plus Y. Similarly, we define scalar multiplication as if C is any scalar, then C into class X is equal to class CX. So, with respect to these two operations, the set X by X0 forms a linear space and it is called quotient space of X with respect to X0. Now, our aim is to make this linear space into a normed linear space. For that, we have to define a norm on this space X by X0, and it is possible only when X0 is a closed subspace of X. So, if X0 subspace of X is a closed subspace, then the quotient space X by X0 can be equipped with a norm given by the formula norm of class X is equal to infimum of norm of X minus Y where Y belongs to X0. So here we have to prove that the space X by X0 together with this norm defined by norm of class X is equal to infimum of norm of X minus Y where Y belongs to X0 is a norm linear space. In some text you can see that instead of X minus Y, X plus Y is written. That is also correct because here Y belongs to X0 and X0 is a subspace. So since it is a subspace, if Y belongs to X0, it is clear that minus Y also belongs to X0. Here infimum is taken over all Y belongs to X0. Infimum of norm of X minus Y is taken over all Y belongs to X0. So instead of X minus Y, you can also write X plus Y. Both are right. Now, let us come to the proof. So, in order to prove that this is a norm on X by X0, you have to prove four things. The first one is that norm of class X is always greater than or equal to 0. And second one, norm of class X equal to 0 if and only if class X is equal to 0. Third one, norm of class lambda X is equal to mod lambda into norm of class X. Fourth one, norm of class X plus Y is less than or equal to norm of class X plus norm of class Y. So, we consider the first one, that is non-negativity property. We know that this norm of X minus Y, this norm is defined on the space X. So, norm of X minus Y is greater than or equal to 0 for every Y in X0. So, here infimum is taken. So, infimum of this is always, it is also greater than or equal to 0. That means norm of class X is greater than or equal to 0. Next, we assume that norm of class X is equal to 0. That is, by definition, infimum of norm of X minus Y where Y belongs to X0. That is equal to 0. Now, infimum of a collection is equal to 0 means that there are infinitely many elements in the set which comes close to 0. So that here we can find a sequence yn in the space x0 such that norm of x minus yn tends to 0 as n tends to infinity. Now, norm of x minus yn tends to 0 means that x minus yn tends to 0, which means yn tends to x. So, here there exists a sequence yn in the subspace x0 such that yn converges to x as n tends to infinity. So, yn is a sequence in x0 and yn converges to x means that x belongs to x naught closure, and it is given that x naught is a closed subspace. So x naught closure is equal to x naught itself. So x belongs to x naught. So x belongs to x naught implies that what is class x? We know that class x contains elements of the form x plus x naught. If this x belongs to x naught itself, then x plus x naught is equal to x naught. Now what is x naught? X naught is the zero element of this linear space x by x naught. So we proved that norm of class x equal to 0 implies that class x is equal to the 0 vector x naught. Conversely, let class x is equal to the 0 vector, that is x naught. So class x equal to x naught implies that x belongs to x naught. Then we have to prove that norm of class x is equal to 0. So consider norm of class x, that is defined by infimum of norm of x minus 5, where y belongs to x naught. Now it is equal to, here x belongs to x naught and y belongs to x naught. So x minus 5 also belongs to x naught because x naught is a subspace. So infimum is taken over. So here we consider infimum of norm of a vector in x naught, and we rename this vector as y itself. So this is equal to infimum of norm of y, where y belongs to x naught. Okay. Now this is equal to 0 because x naught is a subspace. So 0 belongs to x naught. Here we consider infimum of a norm of y, where y can be any element of x naught. Okay. So if you put y is equal to 0, then correspondingly we get this infimum as equal to 0. So we proved that class x equal to 0 if and only if norm of class x equal to 0. Next, to prove that norm of class lambda x is equal to mod lambda into norm of class x. So we consider norm of class lambda x, that is equal to, know that by definition class lambda x is equal to lambda x plus the coset lambda x plus x naught. So norm of lambda x plus x naught, and that is equal to, by definition, infimum of lambda norm of lambda x minus y, where y belongs to x naught. Now this norm is a norm defined on the space x. So here we take the scalar lambda outside. So we get mod lambda into norm of x minus y by lambda. Now again we can take this term mod lambda outside because it is independent of y in x naught. So mod lambda into infimum of norm of x minus, now we consider this vector y by lambda. Y is a vector of x naught and x naught is a subspace. So y by lambda is again a vector of x naught. So we rename this vector as y. So we have mod lambda into infimum of norm of x minus 5, where y belongs to x naught, and this is equal to norm of class x. So we have norm of class lambda x is equal to mod lambda into norm of class x. Next, to prove the triangle inequality, norm of class x plus y is less than or equal to norm of class x plus norm of class y. So by definition, norm of class x is equal to infimum of norm of x minus z, where z belongs to x naught, and norm of class y is equal to infimum of norm of y minus z, where z belongs to x naught. So these two quantities are infimums. Now we consider an epsilon greater than 0. Now if we add epsilon by 2 to these two numbers, then it means that we consider the numbers norm of class x plus epsilon by 2, norm of class x plus epsilon by 2, and norm of class y plus epsilon by 2. Now by the definition of infimum, if we add some number to an infimum, then this will not be a lower bound. So, norm of class x plus epsilon by 2 as well as norm of class y plus epsilon by 2 are not lower bounds of these two sets. So, they are not lower bounds means there exists at least one member of this set which is still less than these numbers, which means that we can find some z1 in x0 such that norm of x minus z1 is less than norm of class x plus epsilon by 2, and similarly we can find another element z2 in x0 such that norm of y minus z2 is less than norm of class y plus epsilon by 2. So we have norm of x minus z1 is less than or equal to norm of class x plus epsilon by 2, and norm of y minus z2 is less than or equal to norm of class y plus epsilon by 2, where z1 and z2 are elements of x0. Next we consider norm of x minus z1 plus y minus z2. By triangle inequality, this is less than or equal to norm of x minus z1 plus norm of y minus z2, and using these two inequalities, this is less than or equal to norm of class x plus norm of class y plus epsilon. So we have norm of x plus y minus z, where z is equal to z1 plus z2, is less than or equal to norm of class x plus norm of class y plus epsilon. And this is true. So, norm of class x plus y is equal to infimum of norm of x plus y minus z, where z belongs to x0. And since this is less than or equal to this one, we have this again, this infimum is always less than or equal to norm of class x plus norm of class y plus epsilon. And this is true for every epsilon greater than 0. So, we have norm of class x plus y is less than or equal to norm of class x plus norm of class y. So, we proved all the conditions, and hence the quotient space x by x0 together with the norm defined by norm of class x equal to infimum of norm of x minus y, where y belongs to x0, is a norm linear space. It is called the quotient norm space. Now, as I told earlier, in order to prove that a function is a norm, we have to prove these four conditions. That is, norm x greater than or equal to 0, norm x equal to 0 if and only if x equals 0, norm of lambda x is equal to mod lambda into norm x, and norm of x plus y less than or equal to norm x plus norm y. Here, we relax one condition. That is, we consider the second one. We know that if x equal to 0, clearly norm x equal to 0. But what about the converse? That is, norm x equal to 0 implies x equal to 0. We relax that converse part. That is, norm x equal to 0 need not imply that x equal to 0. It means that norm of a non-zero vector can also be equal to 0. Now, we are considering functions satisfying these properties, and such a function is called a seminorm. Here we formally define a seminorm. So we consider a linear space E over a field K is equal to R or C. We consider the function P from E to R plus, satisfying these three conditions. So this function P is defined from E to R plus. R plus means the set of all non-negative real numbers. Okay, so clearly if you take any element x from E, P of x is always greater than or equal to 0. So here first condition is satisfied. Now we define P of 0 is equal to 0. That is, x equal to 0 implies norm x equal to 0. That is also satisfied here. And P of lambda x is equal to mod lambda into P of x. P of x plus y is less than or equal to P of x plus P of y. So here P satisfies the conditions for scalar multiplication and vector addition. The only condition that P does not satisfy, comparing with the function norm, is that norm x equal to 0 implies that x equal to 0. That is, here P is a function such that it can take non-zero vectors of E into the 0 element of R. So, we consider the set of all elements of E, set of all x in E, such that P of x equal to 0. And by definition, this is kernel P. We denote this kernel P as E naught. Now, we can prove that this E naught is a subspace of E. For that, we consider two vectors from E naught, that is x and y, and a scalar lambda. So, x and y are elements of E naught implies P of x equal to 0 and P of y is equal to 0. We have to prove that lambda x plus y is an element of E naught, so that E naught will become a subspace of E. So, we consider P of lambda x plus y, and by the property it is less than or equal to P of lambda x plus P of y, and this is less than or equal to, we have P of lambda x is equal to mod lambda into P of x plus P of y, and P of x and P of y are equal to 0. So, we will get P of lambda x plus y is less than or equal to 0. Now, x and y are elements of E naught and lambda belongs to K implies that lambda x plus y belongs to E naught. It belongs to E naught because E naught is a subspace. Lambda x plus y belongs to E because E is a linear space. Here we have to prove that E naught is a subspace. So, x and y elements of E naught implies x and y elements of E because E naught is a subset of E. And lambda is a scalar. So, clearly lambda x plus y belongs to E because E is a linear space. Now, therefore, P of lambda x plus y is greater than or equal to 0 because P is a function from E to R plus. So, this is greater than or equal to 0. So, we have P of lambda x plus y is less than or equal to 0 and P of lambda x plus y is greater than or equal to 0. So, comparing we get P of lambda x plus y is equal to 0. That means by definition lambda x plus y belongs to E naught. So, we proved that E naught is a subspace of E. Now, there is one more property that is P of x plus y.